phone in and I did just like a little 2-second test to see that everything was working and that it saved and didn't crash like it did the other day. It all seems to be fine. The microphone does seem to be recording both sides, so it will pick up Classroom Hubbub. I thought it was only one-sided. I'm going to have to play with the various settings because I'd rather it was just me so that it was slightly quieter and also so that people in the front row don't need to feel they're being recorded. But for today, maybe don't say anything really secret. Front row, just in case you get picked up. Okay, all right. So questions, whatever they were. 9, 10, and in fact 11. All about points. Taking a point in one coordinate system and writing it in a different coordinate system. We're not really terribly interested in points in this course. We're interested in regions. So now we've had a practice on points, let's move on to regions. And I'm going to demonstrate with exercise 12. And one opening sentence just before I do so. Exercises. Focus on points. Focused. How do you spell focused? Two S's, one S. I can't spell, right? I focused on points. Regions are more interesting, or perhaps I should say they're more pertinent to this course. So let me demonstrate with exercise 12. It says describe the following regions in polar coordinates. Now, the meat of this course is integration. Double integration, surface integration, and triple integration, or double integral, surface integral, triple integration. We will frequently be integrating over regions that are two-dimensional or three-dimensional, and you need to know how to describe those in order to get your limits of integration. Those regions are often circular or cylindrical or spherical or some funny shape. And so you need to be able to describe those regions in the best fitting coordinate system for the shape. And that's why you need to be able to describe regions. So what this is doing is giving you practice for drawing up limits of integration when we do double, surface, and triple integrals. So the radius is 2, the circle is centered on the arc, and you want the third quadrant, so that's over there. Okay. So you need to think of that region as being full of points. There are in fact infinitely many points in that region, and what you are going to do is you are going to say where those points are in space. Now we could use rectangular coordinates, but polar coordinates are much better because the region is so circular. So this is a very easy one, but I'm going to go through it fairly slowly. And I tend to think of a ray. I think of these things very geometrically. Very, very geometrically. To me, the picture is the key to it all. I draw a little ray. As I say, this is a very easy one, but in more complicated ones, this method can be helpful. I draw a ray from the origin, has to be from the origin, out to the edge of my region. So it goes through my region to the far edge of my region. And now I need to describe what defines the infinity of points along that little red ray. Between 0 and 2 units from the origin. From the positive x-axis, you always measure from the positive x-axis. Theta is between and 3 pi over 2. Okay, and that describes those points. Notice that if I had drawn that ray anywhere in the third quadrant, it would have gone its maximum length would have been 2 units. That's because my circle is centered on the origin. If my circle were not centered on the origin, the length of my ray might actually be different depending on where I draw it. So you have to ask yourself, would my ray be a different length if I drew it somewhere else? And if the answer is yes, then it means r depends on theta. In other words, r is a function of theta. And you would not expect the little numbers on either side of that r inequality to be numbers. You'd expect at least one of them to be a function of theta. Okay. But that one over there is pretty straightforward. semicircle. There's a circle that's shifted off the origin. It passes through the origin, which is nice. It doesn't have to be out to the point. But the center is up here at 1. We want the upper semicircle up here. Gravity 2 is border axis, is my x-axis. Okay, once again, I'm going to have a ray. I'm going to work this. Okay. I'm going to draw a ray from my origin, not from the center of the circle, from the origin. I'm going to draw a ray from the origin through my region to the far edge of my region. And now I'm going to try and describe, I'm going to draw a squiggle here. I'm going to try and describe the points that are on the ray inside the region. I'm only interested in the region. Okay? So what describes those points? Well, when I ask myself, would my ray be a different length depending on where I draw it? The answer this time is yes. Because if I drew it at an angle close to 45 degrees, I'd end up with quite a short ray. But if I drew it straight up, I'd end up with the longest possible ray. So because it matters where I draw it, it means r is a function of theta. R, there is no radius. R is the r used in polar coordinates, distance from the origin. So how far the points in my region can get from the origin depends on where they are. It depends on the theta value. They can get quite far if theta is around pi over 2, but they can't get particularly far if theta is closer to pi over 4 or 3 pi over 4. Okay, so what you then have to do is a little bit of trigonometry. I am going to... let me actually draw that in red. There's my ray. I'm going to draw it in red, just so that you can see how it matches with my picture. You remember your circle geometry from school, angle on diameter, or angle inscribed in a semicircle. It was at school. 90 degrees. Okay? So if I just close that and make it into a triangle, that's a right angle triangle. Okay? My theta is drawn outside the triangle, but I can flip it inside the triangle. Okay? I hope that is clear to you. And that maximum length of my ray is going to be my maximum value of r. So let me even write here r max. Because of course, all along that squiggly bit, that red squiggle, there are points. And only the ones that are furthest away from the origin are right at the end of that ray. Okay, so that would be my r max. Let's work it out. Little bit of geometry. Let's have a look. That's hypotenuse. That's opposite. I know that opposite over hypotenuse is sine theta. Sorry, sometimes the stylus is a bit slow to catch up with me. I end up with some funny squiggles on the page. There we go. Come on. Thank you. There we go. Yes.
Why do you say r max?
So, because the full length, the point that's at the very tip, what I'm basically working out is how far from the origin is the point that's at the very tip of the ray. So that's why it's r. It's the maximum distance from the origin along my ray. But notice that for different thetas, 2 sine theta will give you different values. When theta is pi over 2, sine theta is 1, and r will be 2, which makes sense. If you draw a ray straight up, its maximum length is 2 units. When you draw theta as small as it can be, which in our particular picture would be pi over 4, sine of pi over 4 is what? 1 over root 2. And then my r max would be 2 over root 2, which is what? It's root 2. So you would expect, so my shortest possible ray, my longest one is about this, and I would expect it to be 2 units long. Cut down to into there, and you'll see it works. My shortest ray would be the one that goes up to pi over 4. Smaller than pi over 4 won't do, there's no theta in there. So pi over 4 is the smallest possible theta. Okay? And if you think about that, if you drew that little ray, if you drew a ray down there, just to the corner of the region, you The maximum length of that ray is dependent on theta. Okay, what about R min? R min will be the point at the beginning of the. I think because I'm right-handed, I always tend to go that way. I have to actually consciously go this way. So I'll try to. I'll try to give that side some love. So now I'm going to have a different picture. Now I'm going to. Sorry, I've drawn that picture a little bit small, but that's kind of deliberate because I'm trying to show that it's a small triangle. It's the one that's I'm going to put up against the region because I'm trying to work out what's the minimum length of my ray before I get up into my region. And another little bit of trigonometry. What do I have there? Hypotenuse is R min, so sine theta is 1 over R min. Little bit of flipping around. R min is 1 over sine, which is cosec theta. Cosec is sometimes just written without the vowels. Question? Okay, I know that the radius of the circle is 1 because I can read it off the circle equation. And I also know that the center of the circle is at 1 plus 1 because I can read it off the circle equation. So I know I'm going to draw a new picture because that picture is Let me draw a new picture. Let me choose a different color. Let's have a look. Let's go for a shade of purple. Here we go. I know that this is 1 because it's the circle radius, and I know that this is 1 because I know where the center of my circle is. And so that tells me that this is an isosceles triangle with 45 degrees all over the place because it's a isosceles right angle triangle. So I know that this angle and this angle and this angle are all equal to pi over 4. Does that make sense? Cool. It's from the geometry of the circle. Yes.
How come for this example we didn't put the right angle on the ray?
Because in this case it wasn't an angle on diameter. That 90 degrees in the big triangle comes from circle geometry, where we know that the angle inscribed in a semicircle, the angle subtended by the diameter, is 90 degrees. That's circle geometry. In that small triangle has got really nothing to do with circle geometry. It's simply the fact that we know our y-axis is vertical, and we know that the bottom of our region is horizontal, and therefore we know there's a 90 degree there. So it's distinct from circle geometry. So there's quite a lot of geometry and trig going on in here. Okay, but I haven't finished. I have to now write down my answer, and what R falls between cosec theta and 2 sine theta for values of theta that fall between pi over 4 and 3 pi over 4. If your theta goes smaller than pi over 4, then my range was and if I go too far, go beyond the 35 degrees, and once again this repeats. Okay, I've made a bit of a meal of that problem, but if when you get to the end of this course, if you go back and have a look at nostalgia at this problem, you'll see that that region there, that semicircle in a circle that's shifted off the origin, comes up over and over and over and over to the point where you see it and you know what that 2 sine theta and that cosec theta just come to you. Yes?
I was just wondering when you have that, when R is a piece angle to get to it, Like we just use the sort of the theta going.
Yeah, no. So if I draw my ray out this way, it wouldn't have changed any of the geometry at all.
I mean, now theta from the positive x-axis is going to be
Yeah, but it would be pi minus theta, and sine of pi minus theta is the same as sine theta, so all the geometry and the trigonometry ends up the same. I always draw it in the first quadrant because everything's just nice and simple in the first quadrant, but all the rules still apply everywhere. Okay, all right, that was 12b. Let's move on to C. 1c, y in x equals 3, okay? Okay, so you can still think of it in terms of rays, but this one you may as well just go straight to the algebra. Could you please keep quiet? Yes? How do I get 3 pi over 4? Because it's this angle over here. So and 35 degrees. It's basically the twin. It's the mirror image of that pi over 4 on the other side. And pi minus pi over 4 is 3 pi over 4. Okie dokie. Catch up with me, stylus. Thank you. Here, just, could you please keep quiet? Even if you're talking about maths, could you please keep quiet when I'm talking? Thank you. So here, just using our little algebraic relationship between x and r and theta is actually quite useful. Sometimes, I almost always, 9 times out of 10, probably more often, 19 times out of 20, I find the picture more useful to use as my guide than the algebra. Every now and again there's a problem where the algebra, what do I mean by the algebra? I mean just by the equations that you have relating your different coordinate systems. But this is a pretty obvious one to go for your equation. X is 3, that means r cos theta is 3, that means r is sec theta. Yay. For what values of theta? Now, you can think of this in terms of rays if you want, but along the way, along any possible ray, there's only one point that's actually in the region, which is different from the other problems that we've done. When we've drawn a ray, it's passed through a region and there's been a range of points. So R has gone from something to something, closest point to furthest point. Here there is only one point. So you just have R equals something rather than R going from something to something. So R equals 3 sec theta, and that's pretty much it, except what's your theta? There's all a bunch of rays there. They're all at different thetas. Well, actually, I've just written something down that's already wrong. Because I should know it. It's probably easiest in this particular case to describe theta going from minus something to positive something simply because of the geometry of the picture. So the rays that are going downwards below the x-axis, they have some sort of minus theta, and I can make that ray get steeper and steeper and steeper. Now the steeper it is, the further it's got to go before it bumps into that line x equals 3. But as long as it's not going straight down, it will eventually bump into that line x equals 3, even if it's like negative 89 degrees. It's going to have to go pretty darn far, but it will eventually bump into x equals 3 because x equals 3 goes down infinitely. And my ray is slanted, so they will meet eventually. So theta can get basically to minus 90 degrees and to positive 90 degrees, but without actually ever equaling them. So theta goes from minus pi over 2 to pi over 2, but no equal signs. Because equal signs would mean straight up or straight down. And then it would never intersect with the line x equals 3. Okay, I'm going to pass that over to you, and you are going to try exercise 30, which is fairly similar. I'll give you a few minutes to do that. In the meantime, while you're doing that, rather than coming around answering questions, I'm going to try and demonstrate something. I'm going to try. We'll see if it works. I've put up something on the Vula site, if anybody has noticed. It's called Padlet, and I'm hoping that it can form a back channel for the class. A back channel is something where you can post notes or questions that actually come up on a screen in the class, and then I can see people are asking questions and I can respond without actually knowing who it was. And I've never actually tried this before, but the class is so big that I'm needing to come up with some bright ideas of how to handle all the questions. So you have a go with exercise 13, and I'll see whether I can get via the PC Padlet to come up on one of these screens. I may not succeed. We'll give it a try. Off you go. Okay, the maximum value of R is confusing a lot of people. If you could please keep quiet. So in that 12b, if we just take another look at 12b, I've had several of you saying it's clear that maximum R is 2. R max is clearly 2. R max is not clearly 2. R max is not the maximum distance that any individual point manages to get away from the origin. If you think about it. Okay, rather scruffy picture. That point over there is 2 units from the origin. It is the furthest point from the origin. Okay? But that's not what you're trying to describe. You're trying to describe your shape. And if you said R goes from 0, if you said, so let's have a look. Minimum is this. The closest point to the origin is that one. It's 1 unit away. So my stylus is being a bit funny here. Come on. R. If you said that, because the closest point is 1 unit away, and the furthest point is 2 units away, what you'd be describing is that. And sure, you could constrain the theta if you wanted to, but you would basically be describing the region in between two circles, because you'd be saying that all the points that are 1 unit away are included, and all the points that are 2 units away are included, and that's not true. Only one point that is 2 units away is included, and it's the one that's a pi over 2. And only one point that's 1 unit away is included, and it's also the point that's a pi over 2. All the other points they're different. They don't fit into that same description of lying between 1 and 2. Which is why you have to describe your R in terms of theta. Because only if your theta is equal to pi over 2, is it a true statement to say that R is between 1 and 2. That's only true for theta equals pi over 2. If you looked at any other angle, your closest point and your furthest point would have a different minimum and maximum. So because you want to have a single statement that describes your entire region, you have to make your minimum and your maximum functions theta. Because your minimum distance and your maximum distance depend on where you look. They're only 1 and 2 if you look straight up. So this statement here is a true statement. That is true. Only for theta equals pi over 2. To say that R lies between 1 and 2 for your entire range of theta. Oh, sorry about that. I jumped onto the next page. If you put theta lie in your entire region, if you said that, that is a false statement. It is not true. What's it describing there? It's that other little squiggly picture that I drew. That false statement over there is describing that picture. It's saying, throughout your range of theta, R goes from 1 to 2. That's just true. I'm not confused how they're trying to describe. Is that clear? So if it's for some connections of values, I actually drew these in check to the back of the calculator. If you look at page 85 in the handbook, you'll see worksheet 1 on polar coordinates. And basically, it's practice in describing two-dimensional regions. I recommend that you do that for homework, maybe over the weekend, maybe even today if you have a free period. Okay. It's worksheet 1, so let me actually write that here.